Hi, everyone. Thanks so much for coming here and being here with us. I will be sharing some really fun topics with you, LLMs in general, intro to LLMs. And I first want to start by thanking GP Tuesdays for allowing this to happen, for bringing together such wonderful community in the AI space. I also want to thank Codesmith, which is a wonderful community that I've had the honor of being part of. I've been following them for quite a few years, and now I'm so happy to be part of their community. So thanks to them for powering this talk with the content that I'll be sharing with you guys today. And my name is Ayleen. As Grant mentioned, I have worked in the tech industry for several years, starting in the business side of things, working on the software engineering side of things. So I want to share a little bit more about AI with you guys. What's up?
Can we pull out the mic? And then
Okay,
you can
sure.
hold it. Yeah, that'd be better. Thank you.
Is this better?
Much better. Yeah, there we go.
Nice. Okay, so as we get started, I kind of want to understand where everyone in the room lands in terms of their knowledge and understanding of LLMs. So on a scale from 1 to 10, using your hands, let's say the scale 10 would be that you work in the industry, you know a ton about LLMs, this is the work that you do day to day, versus 1 being that you don't even know what LLM stands for. So if everyone in the room can show me where you are with your hands. Okay, so I see a couple of 3s, a couple of 2s. I've got you guys, some 5s. I see some 8s and almost 10. Oh, wow, I've got a 10 back there. So hopefully you guys can learn a ton here as well. So I want to start by chatting a little bit about LLMs in general. What does it stand for? Large language models. And it's one kind of AI model, generative AI. And you have probably used these models yourself for the past several years. For example, we've got ChatGPT. You've got Google Gemini. You've got Llama from Meta. And we also have DeepSeek, which some of you might have recently heard about, which is the open source AI model owned and funded by High Flyer Quant, which is a Chinese hedge fund. So these are some of the examples of large language models, but how exactly do they work under the hood? And that's exactly what our talk today will be about. Starting with a couple of building blocks. What is it that makes an LLM work? You can think of these building blocks as, let's say, or think of an LLM as a recipe, and these would be your major ingredients. So starting with data, this is essentially the fuel of the model. The more data, the better the learning. And it also should be diverse and representative of the world around us, of the real world, which we will talk a little bit about later. We also, representing the data, we don't just want to feed raw text into the model. We want to transform it into numbers, embeddings, tokenization, vector spaces, which we will dive into as well. Predicting new data. This is the core job of the LLM. Essentially, it learns patterns from the data that we feed it, and then it generates the next word, the next sentence, or even a whole essay through that process, which we'll also dive deep into. Guiding the model, models don't just run in the wild. We want to fine-tune them with techniques like reinforcement learning with human feedback to make them more useful and aligned. And once these models are trained, we deploy it for tasks like answering questions, summarizing articles, or even generating code, which is one of the tasks that I personally am most excited about when I'm using an LLM. So each of these steps play a crucial role into making LLMs what they are. So now let's dive a little deeper. But before we do that, let's take a step back and chat a little bit about natural language processing, NLP. And essentially, NLP is about teaching computers to understand and generate human language. And over the years, we have seen it evolve across a number of different tasks, which you can see here. You can see some of the tasks here. So starting with text classifications, we know that LLMs can categorize text into predefined labels. So this is useful for things like spam detection, or sentiment analysis, or content moderation. So labeling text, when you think about labeling text, you can label text as good or bad. For example, spam detection, this sounds like something written by a bot versus something written by a human. For sentiment analysis, you might think in terms of this text leans more positive versus negative. Or for content moderation, you might say, okay, this is bad PR or good PR. We also have named entity recognition. And this essentially is where the model can identify names, locations, dates, products. And this is useful for things, let's say, for example, extraction for, let's say, a search query, searching on google.com. A user might have a sentence, but you're actually extracting keywords that will help with finding the exact data, producing the exact results that the user is looking for. We've got machine translation. I want you to think Google Translate, multilingual chatbots, and real-time transcription tools, which can translate between texts in different languages. We've got text generation. So if you think about opening Gmail and seeing that there are sometimes small AI icons that help you with writing emails. This is text generation, which I'm sure many of you have, when you're using ChatGPT, you see this in action. You've got speech recognition. So while these are primarily handled by models that are trained on audio data, LLMs can be very useful in this space because it helps in terms of transcription, for example, for better accuracy and context. You've also got text summarization. I wonder how many of you have gone onto ChatGPT, for example, fed it an entire article maybe, and then asked for a summary. Answering questions, LLMs can provide factual, reason-based answers by retrieving relevant information given the text that they've received through their training data. So we can see LLMs have revolutionized so many different spaces and areas, which has pushed NLP forward and has made it even greater and make even more than traditional approaches couldn't. So that's exactly what we'll explore a little bit next. But there are also other ways in which machine learning, for example, can play a role in our lives. Let's say computer vision. I want you to think Tesla and how the machine is able to interpret the world around it, represent the world around us through objects on the computer, for example. Code generation, something like Copilot on GitHub, or speech and audio, or even science, engineering, medicine. Any advancements in this space is very, very helpful for humanity. So we can see all of the various ways that AI, natural language processing, for example, is helpful to us. So when we're talking about LLMs, I want us to start by thinking about how are we representing that data. So before a model can actually process text, it needs to convert words into something that it can actually understand, which is numbers. And that starts with tokenization. A token is the smallest unit of meaning in text, and this could be a whole word, it can be a subword, it can be even an individual character. So that will all depend on the tokenizer. For example, if we have the word running, one tokenizer might have that whole word as just one token, versus another tokenizer might have that word split into two tokens, run and ning, each having their own separate meaning. So tokenization is that process of splitting text into smaller units, which are then mapped to numerical values, as you can see here in the graphic, which allow the model to really work with them mathematically, which we'll learn a little bit about later as well. So essentially, tokenization is the first step in bridging human language with machine learning. And once we have these tokens, we are then able to transform them into something even more meaningful for the model, which are embeddings. So that is what we'll look at next. Embeddings are numerical representations of tokens, and they express the model's understanding of the input. So each token gets mapped to a high dimensional vector. Basically, it's a long list of numbers, an array of numbers, as we can see here. And the question really is, what do these numbers mean? The tricky part is that we don't exactly know exactly what each individual dimension represents, but we do know that similar words tend to have similar embeddings. This lets us measure the relationship between words based on their positions within the embedding space. So for example, in many models, you might have the vector for king, and the vector for king has many, many dimensions, anything from gender to the role to many other things. So we have a vector for king. You might, in the real world, just extrapolate from there. You know, a king is presumably a man. So you have a king vector, then you have the vector for man. If you were to take the vector for king and subtract the vector for man, and then replace the vector for man with the vector for woman, we might get a very similar vector to queen. So essentially, we have stripped king from it, we have stripped the gender from king, swapped the gender with woman, and it's now very similar in representation through the embedding as queen. And the reason for that is because the model captures relationships like gender, role, implicitly through patterns in the data. So by analyzing these embeddings, we can cluster words with similar meaning. For example, we've got this visualization here. This is a 2D projection of embeddings. In reality, embeddings exist across hundreds, thousands of dimensions, as we saw in the previous slide. But we can still see some form of structure here when we reduce them to something more human-friendly, like this visualization. Now, let's notice how similar words cluster together. So we've got a cluster here in the middle with verbs like walk, swim, and run. Then we've got another cluster at the top, college, school, and work, all related to school, for example. And we even have prepositions like, let's see, on, in, and with, all within their own space. So this is powerful because the model doesn't just memorize words, it actually learns relationships, which are the clusters that we see here. These are representations of the relationships. So that's why embeddings help with things like synonym detection or analogy solving or even multilingual translation without direct supervision. So embeddings are what allow AI to move beyond just processing words and actually understanding context. So in this representation here, this visualization here, we can think of it as another way of visualizing embeddings, and it's in the form of a heat map. Each row represents a different word, and then each column represents a dimension within the embedding space. The colors indicate values. So for example, the red might mean like a higher activation of a particular dimension versus the blue might mean a lower activation of that same dimension across different words. So we look at the words on the left, and we have gender terms like queen, woman, girl, boy, man, king, and queen again, just for the sake of seeing the differences between king and queen here. And we can see that there's some similarity, some relation between the various dimensions across these different terms. Compared to the word water here, which is slightly different from the rest because it's less similar to the rest of the words across multiple dimensions. So this technique was popularized by Word2Vec, which was an early breakthrough in embeddings. And the credit at the bottom here, Jay Alamar, he creates really great visualizations for understanding NLP models. So let's talk about the topic of self-attention, which is at the heart of transformers. If embeddings help the model understand the meaning of words, self-attention is what helps the model understand context. So we're moving from understanding individual words to understanding context, because when you're writing to ChatGPT, for example, you're not just wanting the model to understand the words that you're processing, that you're giving it, you want it to understand the essence of the question that you're asking so that it's producing relevant results. So let's start with taking the word self-attention and breaking it into its subwords, starting with attention. Essentially, attention is, one second. Attention is not 1 second. I was just saying 1 second. Okay, so attention is essentially a way to measure how much one word in a sentence relates to another word in the sentence. So for example, if you have the sentence, the cat sat on the mat, and we're looking at the word specifically sat, and we're wanting the model to understand what sat is referring to, it might see how sat relates to the word cat as opposed to how it relates to the word mat. Is sat referring to the cat or the mat? Well, in terms of understanding context, if we think about a mat, it's most likely not sitting. Maybe you might characterize it or describe it as the mat sitting on the floor, but it's more probable that when you're stating the sentence, the cat sat on the mat, the word sat is more likely relating to the cat, because it's more probable that a cat is sitting or that you're referring to a cat when talking about the word sitting. So attention essentially focuses on the relationship between the individual words. Now, putting that together with self-attention takes this a little further. It allows the model to determine how much every single word relates to every single other word. And this is crucial because meaning in language doesn't just depends on the entire context, not just the individual words like we spoke about. So we'll see how this mechanism works in detail next, but the overall takeaway here is that self-attention lets models dynamically weigh the importance of words. So in this example here, we have a sentence with the word interest, and the word interest occurs twice in the sentence. So the first time it occurs, it's referring to curiosity. And the second time it occurs, it's referring to a financial term, right? And we can really see this because self-attention focuses not just on the word, but the surrounding words. So for the first one, no interest in hearing about, that's where we get the indication that this first word is referring to curiosity. Whereas the surrounding words for the second time we see interest in the sentence, rising, rate, and bank, allows us to understand that it has more of a financial meaning. So this is exactly why self-attention is so powerful. It allows the model to adjust its focus, meaning on the words based on the context, rather than just treating them as isolated units. So let's look at another example here. We've got the dog chewed on the bone because it was hungry. And then you also have the dog chewed on the bone because it was delicious. So the question here is, what does it refer to? And to the point that we made earlier, self-attention allows us to measure the relationship between this word and every other word to determine what's the more likely word that it is referring to. So in this first sentence, self-attention assigns more weight to dog because when you're using the word hungry, it's more likely that you're using it as a description of the dog. Versus in the second sentence, self-attention will shift to bone because when you're using the word delicious, it's more likely that it will fit the food rather than the dog. But yes, this is self-attention, and it's what allows transformers to dynamically adjust their focus, ensuring that it gets linked to the correct word. So this is key reason why transformers outperform other architectures. They don't just process words in order, but they actually look at the context and understand the relationship between words. So this allows them to really generate more coherent, context-aware responses. So the next bit is predicting new data. And at its core, LLMs are kind of like this huge autocomplete system. If we think about the overall term generative AI, it's generating text bit by bit and predicting the most likely next word or token based on everything that came before it. So this process is called next token prediction, and it's the foundation of everything that an LLM does, whether it's writing essays or answering questions, generating code. But the question is, how does the model actually learn to do this? And that's where pre-training comes in. So before an LLM can actually start to generate text, it first needs to be trained. Pre-training is the first phase where the model starts to learn patterns from massive amounts of data that it's fed. So the model in pre-training, what happens here is that the model is fed a huge data set from articles to books, code, conversations, and the goal is to predict the missing word or predict the next word in a sentence. And each time it makes a prediction, it then compares its guesses to the actual word and adjusts its internal parameters based on that result so that it can improve over time. And this cycle repeats across billions of words and thousands of training steps. So essentially, you're refining the model's ability to generate coherent, meaningful text over that process. So another question that might come to mind as we start to think about this training is, what does the model actually remember? And the reality is that the models don't store full sentences or facts like a database does. Like a database, what you have stored in it, that's essentially what exists there. However, with the model, it's essentially compressing patterns into parameters. And a parameter is essentially a massive collection of numerical weights that capture relationship between words and concepts and ideas, and that compression is what we called lossy. And essentially that means that the model retains general knowledge. It doesn't necessarily memorize exact details. So this matters in terms of pre-training because pre-training is producing a base model, and that's one that has a general understanding of language, and it isn't necessarily specialized to specific tasks yet, which is what fine-tuning is about, which I know the next speaker will be focused on. So we'll allow our next speaker to dive into that a little deeper. So in short, pre-training is how LLMs gain their broad knowledge of language, and it's what makes them so powerful across a number of different tasks. So let's dive into a concrete example here. Using NanoGPT, it's a tiny GPT model that is trained on the complete works of Shakespeare. It's a model that has 65 characters in terms of vocabulary, meaning that it learns at the character level and not necessarily whole words. It's trained on about 1 million tokens, which is tiny compared to modern LLMs trained on trillions. So, and it also just has 800,000 parameters and a model size of 9 megabytes. So it's super small compared to a lot of the state-of-the-art models like what GPT is currently on. So the goal here is, if we prompt this model with Queen M, we wanted to predict the next characters. It converts the text first into numbers, tokens, as we spoke about, and then it starts to predict the next characters. So let's see how the model performs and then how it improves over time as it trains. Starting with 0 rounds, we can see here that the model is a bit clueless. It hasn't really learned anything yet, and so when we prompt it with Queen M, it's not necessarily outputting something meaningful. We've got a bunch of random gibberish, kind of unreadable. So the test loss here would be, essentially, test loss is a measure of how wrong a prediction is. So here, the test loss is 4.1, and so this means that the model's guesses aren't very accurate. They are far from actual Shakespearean text. So at this point, it's kind of like a baby seeing words and language for the first time, and it has no real concept of structure or meaning. But as we train the model, let's see how it improves. With 250 rounds of training running in about 12 seconds, we start to see glimpses of structure within this text. Words are still messy, but there are some parts that actually start to look like English. The model has learned better letter frequency. So for example, you can see a few more vowels as opposed to Z's, which are the common characters that are to appear rather than just random ones. And some words start to vaguely resemble Shakespearean texts, but there's still a lot of noise. So the loss right now is 2.4, and this essentially means that the model is improving from the last round, but it's still making a lot of mistakes. So let's give it more time and a little more training, see how it improves. So now at 500 rounds, 22 seconds running, we can see that the text is getting a lot closer to readable English. Words like queen and thy are clearly structured, and some of the lines almost make sense, although they don't all the way. But the model has learned a little bit more about which letters belong together. So it's starting to form more words, and it's starting to generate text that somewhat mimics Shakespeare's style. The test loss is now 2.3, better than the last rounds, and this means that the model is now making better predictions. But let's let it train a little bit more and see what happens. So now we've got 5,000 rounds running in about 5 minutes. The model is producing text that actually starts to resemble Shakespeare. It generates sentences. We can see here it's generating sentences with proper spacing. We've got a lot more punctuation. Words are flowing in a way that almost makes sense. And we can see the meaning is still a little off. So the test loss is 1.6, much better. It's a big improvement from where we started. But let's push it a little further, and let's try 30,000 rounds. So with 30,000 rounds running in about 29 minutes, the model is shockingly good at now mimicking Shakespeare's style. The loss is down to 1.5. So we can see that that means that the model is better at predicting the next character. So sentences are now coherent, the style feels very Shakespearean, and it even follows the structure of dialogue, more or less. But of course, its meaning is still a little bit off, but stylistically, it's looking very close to real Shakespeare. So what does this experiment tell us about pre-training? It tells us a few things. One, it tells us that training is all about gradual improvement. At first, the model outputs complete nonsense, more or less. It was a bit of random gibberish. But as it trains, it starts to pick up more structure, more patterns, and more meaning. It also teaches us that even small models can learn a lot. NanoGPT is tiny compared to a lot of the models that you're probably using in your day-to-day. But it still manages to capture the Shakespearean style. Another thing we learned is that larger models plus more training equals more powerful results. So imagine scaling this up to trillions of tokens with billions of parameters, and that's the kind of scale that our current, let's say, ChatGPT, it's what makes it so good because of this scale. So this is why pre-training is such a crucial step in building LLMs. It's how they develop their broad understanding of language before fine-tuning for specific tasks. So let's talk a little bit about, we've spoken about how models improve over time, but let's break it down to the character level now. So we've got a heat map here, and essentially this is showing that the model assigns probabilities to different characters in order to predict the next letter in the sentences, for example. So at the start, the probabilities are pretty evenly spread. You can see here there's maybe some that are more probable than others, but for the most part, if this is representative of characters, the spread is pretty even. And essentially this means that the model has no real preference as to what comes next. It just starts guessing randomly. And then here we can see the characters being represented. And we see that after Queen M, the model really has no clue what should follow. So it assigns probability across the whole alphabet. But as the training progresses, the model starts to refine its predictions. 250 rounds, you see we're moving from pure randomness to the model actually leaning more towards more likely characters, like vowels or letters that most likely will follow Queen M. 500 rounds, we see here that probabilities are even more refined, meaning that the model has started to better predict and understand character sequences better. So let's say 30,000 rounds. At this point, it's pretty confident as to which letter will likely come next because it has seen enough Shakespearean text in the data to really recognize common word patterns. So this is how a model learns. It doesn't learn by memorizing anything and memorizing exact words, but instead it's adjusting probabilities over time as it's trained to reflect what's most likely to occur based on the data that it has seen. So this might make you think, what exactly does a LLM know? And that's a question you might ask yourself after all of this training. What exactly does an LLM know? And that's a tricky question because unlike us, unlike humans, LLMs don't actually store facts. They store probabilities. When we ask a model a question, it's not retrieving a fact from memory like a database might. It is instead predicting what's most likely to be the correct response based on all of the data that it's been trained with and all of the patterns that it has learned through that training. So this is why sometimes you can say that models hallucinate because they aren't retrieving perfect data. They're more or less generalizing from what they have seen. So fact generation is kind of like this unpredictable side effect of the model, which is great. It's learning to generate fluent text, which pretty much shows us just how well training is working because it's able to produce fact-like text. So this is one of the key reasons that we might use techniques like retrieval augmented generation and fine-tuning to help LLMs really ground their results in the real world and having valid data, verifiable data. So let's look at an example of LLM knowledge in action. We have this sentence, more or less, that we're asking the model to fill in the blank. In Texas, they, meaning people, in Texas, they like to buy blank. And we can see here that we've got several words, like the top words that the model has identified with the highest probability of being able to fill in the blank here. So we've got things, we've got beer, and guns. Makes sense for Texas. The model is essentially predicting the next word in the sentence. But one thing that this makes me want to really emphasize that we spoke a little bit about earlier was in terms of predictions, they're not necessarily reflecting the real world necessarily, they're reflecting patterns that they have picked up from their training data. So this is why we really want to make sure that we're training the data on a variety or diverse set of data so that it's representative of the world and making sure that it's making accurate predictions. So now let's try the same example, but swapping the state for my home state, New York. And let's see what the model believes, what it's going to predict here. So in New York, they like to buy things. Makes sense, because yes, everyone buys things. We've got clothes, books. I'm happy to see books is on this list for New York, thank you. We've got art, and yes, this really highlights a key aspect of LLMs. They don't know facts. The way that we do, the way humans do. Instead, they make educated guesses based on word associations and probabilities learned from their training data. So yeah, this is why prompting matters, because we really want to make sure that we're framing questions in a way that can influence the model to influence the model's responses in subtle but significant ways. So let's chat a little bit about that, guiding the model. So far, we've talked about how LLMs are trained and how they store knowledge. So how do we actually control their behavior to some degree? How do we get the LLM to generate things that are useful, that are relevant, and are accurate to some degree? That's where these guidance techniques come in. So the one we're going to talk about, fine-tuning, essentially you can think of fine-tuning like teaching the general AI model a specific skill, similar to how a chef might go to culinary school in order to learn this broad knowledge, but the chef might learn a new recipe, and it's after culinary school to really refine their skills. So fine-tuning adjusts the model's parameters to specialize for a particular task. And let's say, for example, pre-training, that's where the LLM is really picking up its general language from this massive set of data, like reading from the whole internet, for example, whereas fine-tuning, we're really training it further with particular examples so that it follows instructions better. So for example, if we want AI to write a medical report, we might fine-tune it with real medical documents, and it starts to learn the right tone, it starts to learn the structure and the terminology, so without having to actually relearn a lot of the basic language skills. So compared to pre-training, it requires a lot less data, and it also requires a lot less computation. So it's more about refining the model's behavior rather than teaching it everything from scratch. So fine-tuning is one way to guide the LLM. Next speaker will be chatting about that. But there are other ways we can influence what we're getting from the model. So using the model, for those of you who use ChatGPT or any of these other LLMs, you've already probably done a ton of this, and that's through prompting. So prompting essentially is how we interact with the LLM. It's the process of crafting an input so that we can guide the model's response in terms of the output that we're seeking. And unlike traditional programming, where we give explicit instructions to your machine, for example, prompting is more like programming in natural language, what you might call prompt engineering. So yeah, this is how we carefully phrase our inputs in order to get better results. So thank you guys so much for being here. Thank you, Grant. And thank you to Codesmith for trusting me with delivering this information to you guys.